All right, thanks for the introduction. So title is a little bit of a mouthful. So there are three different things: Lie algebras, quantum simulation, and quantum computation. And I will talk a little bit of all of those. I hope you guys enjoy. So first of all, simulation. So why do we even want to simulate materials? The thing is, I'm basically showing you two different pictures. Like one of them on the left one side is actually a carbon nanotube representing all condensed matter models. And on the right-hand side, I'm showing you a large molecule that is going to be representing the quantum chemistry stuff. So the simulating these materials and simulating the quantum physics of these materials is important because like you have metals, and then when you cool them, they show like fascinating properties such as superconductivity, which in some metals it is shown in extremely cold temperatures, but like in others it is actually like relatively very high temperature. Like in very high temperatures they show superconductivity. And if we can actually just like simulate these materials that crack, ways to synthesize materials that show superconductivity even at higher temperatures, that would be great. Because in that case, you can actually build better transistors, more efficient wires, or even levitating trains. And on the right-hand side, you see a very large molecule that I don't know the name of, but like those kind of molecules are found in biochemistry of like any living beings. And figuring out like, I mean, if a large molecule like this and a large molecule like that, if they're going to chemically interact, what would be the result of that chemical interaction, and etc., plays a very important role in drug design. And then instead of synthesizing those, simulating them is way cheaper and way more safe. Yeah, you don't want to inject something to a living being and then just watch that suffer. So in order to do that, you need to simulate quantum properties of these kind of materials. But that is hard. So even in like these kind of laptops, or even in the the supercomputers that is at the bottom of this building, you cannot exceed about like 20 to 30 atoms, or maybe just like with certain approximations, you can go up to 50 maybe. But if you want to exactly simulate something, you need to be modest. You need to limit yourself to very small materials. And here you see we want to simulate like metals like that, which has trillions of atoms. So how are we going to do that? On a quantum computer, the memory requirement is not like that. So in a classical computer, you add one more atom and you need to double, triple, or like multiply your memory requirement by 10. So it grows exponentially. But in a quantum computer, the memory is handled in a quantum mechanical way. So every time you add one more atom, you just add a constant amount of quantum memory, which in this case we call, I'm just going to introduce you as qubits. So here, the material can be represented as given in the left-hand side, where you have atoms that electrons hop from one to another, etc. And then on the right-hand side, you basically see a bunch of lines that represent qubits. And then the qubits represent the quantum computer here, and then as you go right, the time goes more forward. What I mean with that? So in order to simulate the material, you need to apply certain things to the quantum computer. Like a calculator will not calculate something until you give it instructions. Quantum computer will not simulate the material without you give instructions. So these instructions are called quantum gates that I show you with these little ovals. And these gates will depend on whatever material that you want to simulate. So if your material has electrons swapping from one atom to another, these will be like some gates that will carry the electron from one qubit to another. If they allow those electrons to push each other, those gates will do that. It is material dependent, whatever you want to simulate. However, not everything is rainbows and sunshine. Quantum computers are noisy. So even though you don't have too much memory requirements, the gates that you apply turn out to be not applicable exactly. So there is a little bit of an error in each gate, and that means that as you apply more gates, the error will pile up and you're going to get garbage results. So I'm just going to show you one of them, just so that you understand. Here, I compare two different quantum programs that are supposed to do the exact same thing mathematically. Actually, four of them, but like just focus on the green and the red one. The green one that you see here does the same thing with a lot more quantum gates. And this red one uses only like, I think 20, 30, while this one actually like uses hundreds of quantum gates. And as you can see, like this dashed black line is the exact one. Red one is way more closer to the exact result because it uses way less quantum gates. And then the green one is so far away because of the quantum noise. That is this important. So because of that, my entire research focuses on reducing the number of quantum gates without changing the effect of the quantum program or quantum circuit, as we say. And in order to do that, we use lots of mathematical tools. In order for me to introduce you some of the tools, I'm just going to talk about what quantum gates are. Quantum gates are similar to rotations. A quantum state of a material, of a quantum computer, of anything, can be represented as a vector, which is an arrow in a very high dimensional space. Here I only can show you the 3 dimensions. That's why this is the figure that I showed. And in that case, quantum gates turned into rotations can be imagined as rotations, and the order of these rotations matter. These are not like simple adding numbers together, something like that. So when you have an x rotation followed by a z rotation, it's not the same as z rotation followed by an x rotation. So this shows how complicated these objects can be. And I'm not going to get into the weeds of that, but like there's something that's called Lie algebras and Lie groups that you can actually try to figure out what would be the relations among these things to compress them and then reduce the number of quantum gates. I'm just going to show you one scary equation. Here is the equation that kind of like inspired us to create the work that I'm about to show you. This is Euler decomposition on 3-dimensional rotations. Only thing that I want you to focus on is like there's an x rotation, z rotation, x rotation, and it can be transformed to z, x, z. It's like a change of orders of axes. Okay. So it inspired us this way. So the those 3-dimensional rotations satisfy these kind of relations. We said, what if our like 2-qubit interactions satisfy these things then? Like if you name this thing to be like an x rotation and this z rotation, like all of these things can be transformed into a diagram like this. And then we wanted to figure out in these 2 papers, we wanted to figure out like what would happen if we assume these. And then we found an extremely incredible result that this triangle that you see here is basically the final circuit that you need. Like any other circuit element that comes from the right can be absorbed by this structure if they all satisfy these 2 properties that you see on the top. And how it happens is diagrammatically really funny to watch. So you can basically take these 4 of them to the right, and then so that like they can be away from the other, so it will be easier to see what happens. You can push this one a little bit more forward because they act on different qubits. And after that, just focus on these 3 and apply this rule. You can actually transform that 3 into these 3, and then you can have this guy shoot to the left and just repeat the process. And then eventually you end up having these 2 being next to together, getting can become only one of them. And then you have this, and then when you smoosh all of these together, you end up getting a triangle structure. Meaning that I just prove you if these stuff were satisfied, that these quantum gates can be shrinked down to only this triangle structure. Okay, so this allows us to reduce the number of gates significantly for certain models. Here is a more dramatic picture of it. You can have billions of gates on the left, and then you can have you're going to have like only this triangle structure on the right. So which models satisfy this? On this paper, we also on these papers, sorry, we also shown that like these stem chain transfer field Ising model and transfer field XY model satisfy this. I'm not going to get into what those models are, but we ended up simulating 5-side transfer field Ising model. This was the picture that I shown you, and now you know that the green one and the other one that actually has like lots of gates is a circuit that is like on the left, and the efficient ones are the ones like the one that looks like on the right. So that's why the efficient ones are actually like way closer to the exact result. We also didn't stop there, and then we have an archive preprint that is out that actually extended this thing to like free fermions of 1 dimension, 2 dimension, or like any lattice, any kind of atom structure. That is the 0th order approximation to any metal. So that's why it's very important. And like here you basically see the result of a 4x4 tight binding model, which is a 2-dimensional model. And I introduced you to algebraic compression, and I showed that like it can be demonstrated in any kind of graph, one-dimensional, two-dimensional, three-dimensional, or any. And it uses locally algebraic relations, and we hope that it could be used within purpose of specific quantum compilers, such as like quantum simulation compilers. Well, thank you so much.